Uh, hopefully the semester went okay. We still got a bit of business. So today is a bit, I guess, less structured than it would be in a normal day. We do have a little bit of business to go through, make sure everyone's clear on what's going to be going on with the last assignments and leading up to the exam. Then we can have a bit, and hopefully it'll be a bit more like a discussion. We wanted to just sort of go back through, touch on, the major concepts that we did this semester that you'll need to be prepared to handle on the final. Talk a little bit about, okay, when you're suddenly faced with everything at once, how do you actually figure out how to proceed when you're doing a problem or something? Okay, so first, business. So the quick reminders, right, for assignments, homework, the last one, it's pretty short if you haven't looked at it, but the last one's due on Thursday, and the short paper on process of science is due on Friday. Another thing, the course evaluations are now online. Unfortunately, we don't know hardly anything about how to connect to those because they don't seem to tell us anymore how that works. But please go fill those out. Let us know how things went. Yeah.
Are they on
Then the
Blackboard?
final exam is next week. But we have a bigger schedule than that this week. So this is all the stuff going on in more detail. So that was like the major bullet points. The detailed schedule is this slide. So we're also going to have a lot of help hours to help you prepare. So hopefully everybody can connect to one if you need it, or as many as you need. So that starts today, 3 to 5. It'll be in the Zoom clinic with Walter. Tomorrow, remember, so today is the last day of class. There's no recitations tomorrow. But we'll have an 8 to 10 a.m. in the morning in the clinic. So we got afternoons and we got mornings. I'll be doing the session on Thursday afternoon, which we'll do in Blackboard Collaborate here instead of in the clinic. And then we'll have the same. Well, I'll have that as well on Friday in the afternoon, and then on Saturday with Walter at night. So hopefully those hours work for everybody. We have a few different ones. Then the way the exam is going to work is it'll be posted in the morning on Monday and due at the end of the day on Tuesday. It'll be on Blackboard again. And just a few more details on the final exam. Take home like exam 3 with a few full problems to be scanned and submitted like you did before. But we decided after the experience we had grading and everything with the last exam, we decided we'd also have a few additional multiple choice questions on Blackboard. So this will actually be on there where you have to use their web interface. So that'll be one piece, but then there'll also be pieces that you have to handwrite and scan. The exam is a cumulative exam, right? But we did stuff since the last exam. So you'll definitely have questions on anything that we covered since the last midterm, but there will be more than that. And sometimes you'll have to mix different things in different parts, right? We'll talk about the different sections of the class through today.
I mean, I imagine we're going to try to weight the exam toward questions that tie together the entire semester, right? Things that are about, okay, what are some of the principles that have run through the entire semester?
Yeah. Right. Oh, and I didn't put it on the slides, but we did, because we have this new bit with the multiple choice. We wanted to give you some examples, so we did go ahead and we're going to be posting a practice exam today, if you want to take a look at that to help you prepare over the next week. So you can see a few examples. It won't be exactly what you'll see in the final necessarily because we haven't written those yet, but hopefully this will give you an idea of what those kind of questions might look like. Oh, Okay, did anybody want to ask about the business parts? Ah, it's up. Okay. Mhm. It's all clear to everybody exactly what you have to do. um, yeah, how do you calculate your grade? The problem is, right, we have a bunch of different parts. Um, and so it's difficult for us to do it. Yeah, because we dropped the lowest of everything. You should be able to do it yourself if you follow um, the description on the syllabus, right? So if you go through and drop your lowest exam grade and then do the weighted, you have to basically say, oh, if I got 80% on this exam and it's worth 15 points, right? Then I got that's um, what 12 points. um, yeah. So and you have to go through it and do that. In terms of other parts where you're not sure, like the pre-lecture questions, I'll need to do over the next couple of days. You just go through and basically, if you had any reasonable point total on that, you get 100%. Other than that, we're trying to get the TAs to finish all the homework grading, but it's not all done yet. So unfortunately, you'll have to sort of guess at what that will be based on what you've gotten before.
I found as a general rule, if you want something that's likely going to be pretty close to your final grade, assuming that you've been keeping up with your homework, assuming that you've been doing your other work, if you drop your lowest exam grade, average all of the rest, and then add a half of the letter grade, then that's usually pretty close to people's final grades. Because the exams tend to run a little bit lower and the other things tend to run a little bit higher. Also, I've gotten a bunch of questions about can you drop the final as your lowest exam grade? If you look at the syllabus, it says that since the final is normally worth twice as much as a regular exam, if the final is your lowest exam grade, then rather than dropping it, we will only count it the same as your other exam grades. So really, we think of you having 5 exam grades where the final counts twice. And if the final is the lowest, then we'll just drop one of those two. But yes, the final will count at least in some part for everyone.
Yeah, sorry about that. I know it can be frustrating with the grades, but we have so many different components of this course. It can be it's tough for us to calculate it too, right? So that you have to write a script afterwards and do it. So Blackboard's tools are not super great at doing this properly. Okay, so all right, so everything's good there. I basically the way this is going to work, and I guess Walter, you can jump in if you want to say anything as we go. I just sort of made an outline, to try to hit as sort of reminders, right? What I think the major ideas of what we're doing in the class are, and give some pointers about how do you think about approaching problems when you don't know exactly what you're supposed to do on them because it's not that you're just on this one unit with this one week and you're only doing one kind of problem. So first, the way we broke it down, right, is we had 4 sections of this class, and that kind of goes into 4 main parts, right? And so we spent the first bit, we did motion problems in 1 and 2 dimensions, just describing how things moved. And then we talked about forces and why things actually accelerate that gave you that motion. right? But then we saw that, force problems can get really complicated. And sometimes you don't even know how to figure out what the forces are. And so you look for things to simplify that, right? And so that's where we brought in work and energy and momentum, right? And then in the last bit, we did rotation, which is basically just have analogs of all these things. So we talked about rotational variables and kinetic energy and torque and angular momentum. And so how do you figure out what to do, right? If you're on the final and you have every single kind of problem, for a few general tips, and then as we kind of go through the outline, we can say more specific things about different kinds of problems. I think the one thing that really stands out to me about how, what gives you a clue about how to approach different kinds of problems is to think about what's going on with time in the problem, right? Because if you need to find motion over time, position as a function of time, it's pretty clear what you need to do. But sometimes we also had problems that were about a single instant of time. What's happening right now? What force is on it right now? And we had other problems that describe sort of a before and after process, right? That you had one situation and then something happened and it was complicated and then you had an after, right? But you can learn something about how things were after or before. And then also to think about how complicated it is, right? Do you think you could describe all the forces involved, right? We know about certain kinds of contact forces, right? And we would do force problems, but we talked about collisions and things were basically too complicated to write down all the forces, right? And so you can just sort of think about those two things, and hopefully that starts to give you a hint about how you should approach that stuff. Okay, and like I said, I mean, I don't have a lot for today, so jump in with questions if you have them. Okay, so about time. So the first thing we did, right, was the kinematics. So just describing how something moves. And the things that you needed, right, is you needed to know the acceleration, and then you needed to know where something was and how fast it was going, or its velocity and what direction it was going, right, at some time, right? And then you could describe the motion for all times, right? But you had to know the acceleration for all times, right? And then, we didn't spend a lot of time doing complicated integrals, right? So mostly we start to constant acceleration problems, right, where you have these kinematic equations, right? And so this is really about, goes back to that general tip. Think about whether you need to know something about time, how something, the details, right, of the path something takes over time. Right, so you can use the kinematics to solve problems where you know how it's accelerating, where it was, and what its velocity was, and you want to know something about the future, right? And so this means, for instance, you might be doing a problem and you might just have one part of a larger problem where you know this, right? Like you have something gets shot out, like a projectile. We did all those projectile motion problems, which were kinematics, and you could do an energy problem that would tell you how fast it starts out and where it starts out, right? But then you can actually do, as a function of time, you need to actually map out the path to see what's going to happen to it, right? And so basically, that's, this is your tool to do that. So if you need to actually worry about the path something takes over time, not just one moment before and after or just one instant in time, but the whole path, right? So when you need to know about the whole path that something is taking, not just what's going on at one instant, like what are the forces causing acceleration at that instant, and not just a before and an after, right? Where you know the situation before and after, because that's like what the energy problems do. But if you need to know, okay, I know this one instant, and I know the acceleration for all the times because it's constant, and I'm going to figure out the path something is going to take, right? And that's when you're going to want to do kinematics. So there's an example of this where you have to do this for one part on the practice exam. that you'll see it, but it mixes in, A and B, different things. I don't know. Did you have any other thoughts, Walter, about that?
I do. So there's one case that's sort of deceptive where you have a question, and not deceptive, but you have to think clearly, where you have a projectile and you're trying to figure out how far it goes, right? And someone goes out and they throw a ball at an angle of such and such above the horizontal. How far does it go? And we did this problem a bunch in the kinematics segment of the course, but you might say, oh, well, I have a before and after state, right? I know I threw the ball from here. I know it lands over there, and I'd like to know where that is. So you might say, that means I should use conservation of energy. But you actually can't, because a final state where the ball has traveled 20 meters and a final state where the ball has traveled 30 meters both have the same gravitational potential energy. The thing has come back to the ground. So you cannot use conservation of energy to figure out how far something travels as a projectile. Another kind of indication.
Well, and actually, I will say, Walter, just to interrupt you, that's one too, though. Like, one thing is, don't get discouraged sometimes if you do head down the wrong path for a little bit. Right? That's an example where you could say, oh, maybe I should use conservation for energy for this. Well, I'll think about what's the energy before, what's the energy after, and then you look at it and you say, oh, wait, the energy after doesn't tell me anything about how far an exit went.
Exactly. Right? Exactly.
And don't freak out and get discouraged if that happens, right? Maybe take a step back and say, wait, should I have come at this problem a different way?
My experience in grading literally thousands of Physics 211, actually tens of thousands of Physics 211 exams by this point, is that students often spend too much mental effort on doing an approach that they think of and not enough mental effort on thinking if that is the right approach. So don't be, exactly as Professor Rudolph has said, don't think that there's anything wrong if you say, maybe this won't work. Maybe I have to go do something else. And we all make mistakes in algebra. We also can all make mistakes in what approach you take, and that's fine. But as he said, if something's not working, reconsider.
And you were going to say something else, and I interrupted you. So
it was just that, actually, about the when you have yes, I remember what it was now. If you're concerned, remember that energy is a scalar, right? So often if you are concerned about the exact vector nature of something's position, then that can be an indication that you should use kinematics. Unless the exact vector position connects to the energy in some way because of the forces that act on it. Another indication that you should not use kinematics is if the acceleration is not constant. Remember, those formulae are only valid for constant acceleration. So if you have an object sliding down a ramp, you could use energy or kinematics if it's a straight ramp. But if it's a curvy ramp, then the acceleration is not constant, and these techniques won't work. Unless you want to do far harder algebra and calculus and differential equations than anyone wants to do.
Yeah, and a lot of times, even if you're good with the calc, sometimes you get differential equations for those that are actually not solvable with a pencil and paper. So fairly simple problems can give you complicated differential equations sometimes. Okay. Anything else? I think that was, I just put about kinematics. Like I said, I just made an outline of topics to talk about. So if there's any other questions, does that make sense when you might want to use kinematics? All right, then. So let's talk about the next thing we did, right? The next thing we did was forces, right? And sort of the key thing about the force problems we did, right, in terms of, free body diagrams and Newton's laws and all that, right? They all talked about what was happening with an object at some instant, right? Because we wanted to simplify it and say, what is going on with the forces right at this one moment? Now, either that meant you knew the forces and you wanted to find the acceleration, right? Or you knew how it's accelerating, like when things were moving in a circle, right? And you wanted to find the strength of the forces that caused that, right? And occasionally we would do force problems that we'd say, oh, we figured out what's going on at this one instant, but since all the instants were the same, because it was like sliding down a straight ramp, right? Then the acceleration was the same and you could just do that into the future. So occasionally, like there was an element here that involved some longer times, but generally it's actually connecting the forces back to the kinematics if you're doing it that way. Or to the energy, right? We figure out, oh, the forces are always the same as it slides down the ramp, and so you can figure out the work, right? But in terms of talking about analyzing forces, right, we always would sort of single out a single instant in time, right? And that's sort of what's different about it compared to some of the other ways we thought about problems, you know. And so I did want to say, so sort of like we had the kinematics equations, where if you knew some things, you had these equations, you did that, right? Forces have their own strategy that you should do, right? Where you needed to actually sit down, figure out what the forces were. Drawing a picture helps, right? Make a free body diagram, right? And then you had to break everything up into components, find all of those for all the forces, and then you sum up all the forces, right? And say that that's equal to MA, right? In X and in Y. We don't generally do that many three-dimensional problems with Z. And then you had to think about what you knew about the forces and accelerations, which isn't always like, oh, they gave me the number in the problem, right? Sometimes you had to do some extra formula, like you had to put in friction relation to the normal force, or there's a spring force, or you knew that the acceleration was v squared over r because it's going in a circle, right? And then once you have everything that you know put in there, you can solve for whatever it is that you didn't know and you wanted to find, right? Yeah, but again, right, the point was basically you're always talking about analyzing some instant in time. It just might be that there's lots of instants that all follow the same rules. So pause if there's any questions or if Walter wants to have a few words.
No, I'm actually, so folks, I'm creating a grade calculating spreadsheet that I will post. So you can type in all of your grades to this spreadsheet and it will tell you what you get. So I may have that done by the end of the class.
Okay, so hopefully everybody's clear on forces then. Next thing, right, so after we did forces, we started thinking about what would happen over some time, you know, so you sort of let the forces go into the future, but you want to take complicated situations where it's difficult to analyze what's going on with the forces because you don't know the details of how it happened. But you can still simplify things into sort of a before and after problem, right? And so this is where we started using energy and momentum, right? And generally this is sort of key, like it's before and after, which, you know, sounds like just two situations, although we saw, right, sometimes there's like three situations where it's before, middle, and after, right? But there would always be, in some sense, a period of time where something complicated happened that we couldn't figure out the details of, or we didn't want to figure out the details of. right? Because two things would collide or they push off each other, right? Which can involve forces that are constantly changing, right? But still, we knew that if that happens, and it's just the forces are between the two objects colliding, that you could use momentum to figure out how the before situation and the after situation were the same. Right? Or you had something moving over a complicated path, right? Like a funny shaped slope, but you knew the energy was conserved, right? And so then in that case, you can relate sort of before it slid down and after it slid down, via the energy. So I did want to bring up a few details of things you can ask yourself again about momentum and energy conservation, right? And they were essentially, for momentum, how do we know if momentum is conserved? So almost all the collision problems we did, right, momentum was going to be conserved. So it's almost always yes, but might as well think about, again, how you reason that out, right? So basically, is there a net external force on the system? And remember, for momentum, it was important that all you had to worry about was the external forces. And if there's none at all, then momentum is conserved. And the same for torque and angular momentum. We'll come back again about the rotational stuff. But even if there is an external force in the system, like say that there's friction on the ground, but two things collide, right? If that collision happens essentially instantaneously, then we also say that use momentum and angular momentum conservation, right? Because essentially you can break it up into two pieces, because the external forces only change momentum based on how much time they acted, right? You had to get that impulse where they had to act for a long time. And so generally in the collisions, right, momentum was always conserved. The only time momentum is not conserved, right, essentially in our class, is because, something is sliding along the ground, right, and friction is slowing it, or it bounces off the wall and you're not keeping track of the momentum of the earth that takes the moment. When the momentum gets given to the wall, it goes to the earth because they're connected. Right? But energy conservation, remember, was a little bit more complicated, right? Because you had to think also about what's going on inside the collision, right? And so one way to say energy was conserved is because literally the only forces acting were conservative, right? And conservative meant we could write down a potential energy. So we basically had gravity and spring force for this class, right? And so if you were in a situation like something is just free falling under gravity and there's only gravity on it, that's conservative. Or actually something was on a spring and falling and under gravity, right? So like the spring force was the only force acting besides gravity, then the only forces acting were conservative, and you can say yes, energy is conserved. But if there's other external forces, we always have to check if they're doing work, right? So we had a lot of situations where, say, there was a normal force for something sliding, or the tension and the pendulum, where we knew things didn't work because the force was always perpendicular to how something was going to move. Now, sometimes energy is not conserved, but you still want to think about the work that's lost to a force like friction, right? And then otherwise, so you can figure out exactly how much it's not conserved. That's another thing you had to do. But sometimes you couldn't quantify it exactly, and so you would just say, I know energy is not conserved, because like, for instance, when a collision happens, I mean, unless you know it's elastic for some reason, like you're told that, right, generally you will lose energy in a collision, or gain it if it's more like an explosion, right? And so definitely energy conservation takes a little bit more thought than momentum, I'd say, right? But the point is both of these, right, involve these sort of before and after processes, right? You have before a collision and after a collision. You have before something slides down a ramp and after something slides down a ramp. And generally what happens in the middle is something that you can't sit down and do the force diagrams for, right? Because when you have a collision and something is sticking together and getting, stuck with the Velcro, and maybe it's even compressing a little bit, and it's just a mess. And you can't sit down and figure out what direction the forces should be at every instant in time. So that kind of points you towards wanting to use energy and momentum, right? So the difference here with respect to like kinematics was in kinematics, you knew what was going on the whole time, right? And you wanted those details. And then the force problems, you sort of picked out one instant of time and thought about it. And then here you're doing a before and an after, and in between something sort of complicated happens that you can't figure out easily anyway.
Can I comment on the energy methods,
Yeah.
Matt? So often I get questions from students about kind of comparing the ideas of conservation of energy and the work energy theorem. And they kind of say the same thing because potential energy, in a way, is just accounting for how much work a certain force would do if something happens. So, my approach to thinking about whether you can use energy methods for a problem is my checklist is to use energy methods. Number one, you need to not care about time. Remember, energy is conserved, so that means it doesn't change with time, so you're not going to learn about changes over time through energy. Um, and also, work is force dot distance. There's no time in that anywhere. Um, you need a clear before and after picture, but you also need to somehow be able to account for all the forces that do work. And maybe you do that accounting via potential energy. If it's a spring or if it's gravity, we have formulae for potential energy for those. Maybe you do that accounting by just directly calculating the work that they do. By saying, okay, work is force dot displacement, and I know, the thing is traveling on some path with some known force, and I can calculate what work that is. But regardless, you have to be able to account for the work done by all forces. Um, that last the bullet point that Professor Rudolph has on his slides, that signals that you should use momentum instead. Whenever you have two things colliding, but you don't know how big the force is between them.
Right. And actually, I wanted to reiterate a point which I think we mentioned earlier in the sort of overview. So Walter just said about how like you want to quantify the work that's being done, um, over the process. So while it's before and after, that does have a sense of um, you don't or like you kind of know what's happening in the whole time. So even though you don't care about what the number, how many seconds t is, you kind of still had to figure out what's happening at all times. And so there is a bit of a gray area there where like you can do some of those problems with kinematics where you write down the t or without or with just work, by doing force and displacement. And generally that's actually because, right, you end up with you're just doing the kinematics, but you solve for t and then substitute it out, and you never resolve for it. But still, there's some problems that you'll do where it's still just easier not to think about the kinematics. So, for instance, we had problems, right, where something was swinging, like a pendulum, but there was also another force on it, right? It was, say, horizontal. And so it was still fairly easy to figure out the work done by that force, but maybe you didn't want to figure out what the acceleration was at every point along the path. Which you could have done, but then you would have had to integrate it up and figure out exactly what's going on if you want to do kinematics. So I guess my point is there is a bit of a gray area there where they seem very similar, but you're trying to. I guess what I want to say is yeah. So sometimes though it's easier to do the work because the fact that the directionality of the dot product part of the force and the displacement is important. I don't know if that made sense. Okay. So, all right. So if there's no questions, yeah. Oh, I did actually write down a little strategy thing for collision problems. I kind of forgot about that. You know, again, right? So this is the before and after, like we talked about. Sometimes there's multiple steps, so it's like a before and then a middle and then an after, where there was like a collision that conserved momentum, and then you figured out how fast things were going after that, and then they slid, and you had to figure out how they lost their energy or transferred their energy into potential or something like that. Right? And then you just use your equations to relate before and after, right? That momentum in X and in Y if momentum is conserved. And so remember, there's not just one momentum with the magnitude of the velocities, but there's a momentum for every direction. And then if energy was conserved, you'd have the sum of the kinetic and the potential energies was the same. And sometimes, again, you could figure out the work, and so you could figure out the difference between the before and after energies. And then every once in a while, you did need a little bit of extra input to solve things like you had a quadratic equation, and one of the solutions was the bumper cars or whatever, and they pass through each other is one of the solutions, and so you don't pick that one. It's like, but generally that's the idea. So so a lot of times, again, in step two, you're either going to be doing momentum or energy conservation. Right? There's generally going to be some hint if you're doing a collision where both apply, right? Like you're told that it's an elastic collision. I'm trying to think if this. I don't know if I can think of a good example where it wouldn't be sort of just given that you can use that you have to use both at the same time, right? Because it depends, right, on the details of what's happening internal to some two things colliding, which is, like we said, is complicated, right? And so if the complicated answer is yes, energy is conserved, then you just kind of have to be told that, I think. Is there any example that's different, Walter?
Different in what way?
That you would just have to know that energy is conserved but in a collision without being told.
Um, I mean, that is perhaps in particle physics where all collisions or almost all collisions are elastic, but not generally. I mean, generally,
Right.
if something is an elastic collision or not is determined by complicated material properties that are outside of the scope of this class. Now, we might go the other way like we did in exam 3, right? In exam 3, we said, here is a collision, you tell me if it's elastic or not, where you had to use conservation of momentum to figure out where all the objects went, and then determine for yourself whether kinetic energy was conserved, right?
Right. Yeah, no, and that's a good point too, because that was a pretty common thing that people didn't think about it that way. That I can just check, right? But yeah,
And that problem, that was probably the most common source of serious physics errors on the exam. I mean, people did really well on exam 3, right? But one of the biggest mistakes that people made was seeing that collision problem of the two balls or whatever it was, three balls, two balls, and said, oh, I'm going to use conservation of energy here and figure out the unknown velocity. And you couldn't do that because you didn't know a priori whether this was an elastic collision or not. In all collisions, momentum is conserved. So you needed to use the conservation of momentum to figure out the final velocities of things and then check to see if it's an elastic collision, but you cannot assume that unless you explicitly know that for some reason. Like if they are elementary particles colliding, you can pretty much assume that momentum is conserved.
energy, you mean, but yeah.
Yes, energy. Thank you. You can always assume momentum is conserved. And all of these problems are just kind of going backwards and forwards through the same sorts of ideas, right? You all remember the problem with the dog jumping off the boat in exam 3? Um, this was a problem where what you knew going in was you knew that energy was not conserved. This was an explosion. You have two objects separating. And what you knew going in was how much extra kinetic energy is created by the dog's muscles. And most students that people's papers that I looked at, I didn't grade all of those, but I graded some of them, were able to figure that out quite directly, to say, oh, this is how much energy, how much kinetic energy I know is manufactured after the explosion. But it's all going to be the same kind of thing, right? You know enough about the velocities to use conservation of momentum to determine where all the energy goes, or you know enough about the energy to find more unknown velocities. Or maybe you just don't care about the energy, which is true in a lot of inelastic collisions.
Yeah. Actually, no, wait, I did think there is one example where you need to bring extra knowledge for this class and say in the collision that energy is conserved. And that's when the collision completely happens through a spring. Because in that case, the internal force of the collision, like if they bounce off each other on a perfect spring, um, that conserves energy.
Right.
But that's the one specific one. And it's just because that in that case, you know the nature of the force.
Right.
Because that's really what it's about when you say that energy is not conserved in the collision. It has to do with the nature of the forces, essentially,
Yes.
between the objects.
Yeah. I mean, in a way, saying energy is not conserved, the equivalent statement is, I don't want to think about where all the energy goes because it's hard. Right. It's going into breaking atomic bonds and twisting pieces of steel in a car collision and jiggling atoms around and turning into heat, and we don't want to think about that. But in the case of a spring, we know how to think about that.
Okay. So the last little bit we did was rotation, and I don't have a big thing about rotation because we just spent the last 2 weeks talking about it. I just wanted to remind you again that the analogy to one-dimensional motion. Um, that if we're basically always talking about things, rotating around in a plane, just because it admittedly gets ridiculously complicated as soon as things start rotating in arbitrary directions. And that's basically the same as a one-dimensional motion. And so you have this full analogy with the position and the angular, position versus angle, mass and moment of inertia, forces and torques. You have momentum, angular momentum, and kinetic energies, right? And so there's basically a complete analogy that all the stuff works basically the same way. So you can ask yourself questions about like conservation of angular momentum is basically the same as the conservation of momentum we just spent a few minutes talking about. It's just that you calculate it differently, right? And like I said, I don't have a big thing to review about that. We've just been doing it for 2 weeks, so it should be fresh in your mind. But yeah, definitely you'll have to know about rotation. So I wanted to at least make sure it was represented on the slides. And so now I think this is just a time for you. If you have questions, if there's something that you're confused about, especially if it's about, like you saw a problem and you were trying to think, how do I approach it? It's a good time to spend a few minutes and we can go through that.
We have lots of time here. I have some stuff to say too. I have some slides of my own, but we have plenty of time, so please ask questions. If there's a whole topic you want to review, if you just want to say, hey, can we go back and review power or the quadratic formula or vectors or anything like that, we are happy to do that right now. Sure, Kim. Matt, would you like me to doodle some stuff out? Because I can doodle in real time.
Yeah, that'll work.
All right. Exam 3, question 2. All right, we will take Kim's question, and then we will do that one. Give me just one moment. Okay, so this was kind of where I was going to enter my slides. Let me just get a new page here. New page after. And now we need to set it to something like that. Okay, so dot products are a general idea in all of vector geometry, but we use them here to calculate the work done by forces. So here I'm going to first talk about the dot product kind of in a very general sense because, so Kim, you're an aerospace engineer, right? If I recall. Um, so you'll be using this idea quite a bit for all kinds of things. So, for instance, when you're thinking about the dot product of the direction that an airplane is pointing with the direction that it's moving, that dot product comes up in aerodynamics. So generally, if I've got two vectors, we'll give them names here in just a moment. We'll call them A and B. So here's vector B, here's vector A. We first encountered the dot product in the work energy theorem. We had, or we saw that work was the x component of force times the displacement in x plus, oh, come on, stylus, times that. And we call this the dot product of F with the displacement. But what does that mean? So we got there by thinking of the sum of the x components multiplied together plus the sum of the y components multiplied together. But we saw, like 2 slides after that, that there are really 3 ways of calculating what A dot B means. So what I'd like to do now is I'd like to think about each vector, consider its components parallel to and perpendicular to the other vector. So I'm going to draw a couple of dotted lines here. That's the component of A parallel to B. And then here's the component of A perpendicular to B. So let's draw those in. So this is A, whoop, I don't want dotted text here. So this is A parallel to B, and this is A perpendicular to B. And I can do the same thing on vector B. So here's the component of B. It goes a little longer than that. There's the component of B parallel to A, and there's the component of B perpendicular to A. So B parallel, that one is B perpendicular. So I'm doing it this way because this will also help us review the cross product. Let me draw my vectors one more time. Let's see, that's 6, 2. But this time I'm going to draw them with a common origin. Like this, and label the angle between them. So if this is vector B, this is vector A, and then in red, I'm labeling theta, the angle between them. Here are all of the things that I can do with this. So here's the setup. So let me make this go away now. So the dot product A dot B, and this is used to find work in our class, you can calculate it 3 ways. It's either A parallel times the magnitude of B, or A times the component of B parallel to A, or If it's easy for you to find the angle between, it's a times b times the cosine of the angle between them. And you may use any of those techniques. Um, Often, one vector is always perpendicular to the other. So if you imagine, say, something sliding down a ramp, the normal force is always perpendicular to the motion. So it does no work, end of story. Or if you have something sliding down a ramp, so if you've got some ramp and an object goes from here to there, so the work done by gravity is the force of gravity times the displacement parallel to that force. Well, that's just going to be mg times the distance moved down, because that's parallel to gravity, and that would give you mg times this distance h. So that's one example of how that comes up. People were asking about cross products as well. So Kim, I know that wasn't particularly your question, but I can certainly talk about that. Let me ask first, so Kim, did that help? That review of the ways to calculate the dot product. Okay. So for everyone else, and for everyone, the cross product this is just used to calculate torque. We haven't written it with an X. So Matt, did you ever use that notation?
Yeah, I think it was on the slides
Okay.
at least. I brought it up. I mean, because I think I even said though that this is mostly important to think about the vector nature of it, and um,
But
mostly going to be needed for 212.
yeah.
But
But this is just the opposite of that. So finding torque, it's the perpendicular part of one vector times the other. Now, the cross product in 3 dimensions has a funny property, and these formulas just tell you the magnitude of the cross product in 3 dimensions. You'll need that for 212, but you don't need that here. So any questions about any of that before I move on to Kalhaku's request for exam 3, question 2?
I just want to reiterate your point, right? That again, these things are, it's 3 ways, but I hope you can at least sort of get the intuition why these are the same, right? Because if you drew the triangles when you start the vectors at the same place, right, you'll see that for the dot product, when you want to find the parallel, it's the one that's adjacent, right? Because A and B are sort of next adjacent to each other, right? But the perpendicular component's the opposite part. And so that's why the cosine goes with the dot product and the sine with the cross product. But yeah.
Yeah, that's just the trigonometry. Yes, I need breakfast. So there was a request, I think, for exam 3, question 2. So I can certainly load that. Well, all right, give me 1 minute to find that. Okay. So Kalhaku, this is the question you wanted to do? All right. So you tell me what to do. What technique should I use to find the velocity of the ball after it leaves the launcher? So, what are our options? We could use kinematics. We could use energy. We could use momentum. it was momentum and then energy. So what's the suggestion here to use momentum? What part of this problem indicates that momentum is the right thing to do? Yeah, yeah, because we know the um, energy associated with an uncoiling spring, and momentum here, since this thing is mounted rigidly to the ground, you can kind of think about how this problem, the situation manifestly doesn't conserve momentum, right? Because I have the launcher doesn't move because it's mounted rigidly to the ground. There's no momentum in the beginning, but there is momentum afterwards because the ball gets shot out of there. So I don't want to use momentum because it's not conserved. Kinematics is going to be hard, at least while the ball is in the launcher. So energy is the right thing to use. Um, Now let me be a little bit more careful in drawing the initial velocity vector, right? So here we're trying to find v naught. So if I use conservation of energy for the ball leaving the launcher, I have my standard formula for conservation of energy. And here I know that there are no other forces doing work. Um, Matt, I just lost one of my monitors. I can finish this problem, but after I do this, I'm gonna have you talk for a bit while I fix something. I have a hardware fault on my end. Um, so that's zero. I know in the beginning there's no kinetic energy. So in the beginning, the potential energy is 1/2 kx squared, or k delta x squared. It's compressed by 5 centimeters. I'm going to call that x. Um, there's no potential energy in the beginning because, or excuse me, that is the potential energy in the beginning. There's nothing else doing work. And that's being converted entirely into kinetic energy, so that gives me 1/2 mv squared. Um, the final potential energy, so here, final means it leaves the launcher. And part of the instructions for this problem are to ignore the height difference between the ground and where the ball is fired. So I don't need to think about the ball moving upward very slightly as the spring uncoils. So here the velocity was just x times square root k over m. That gives me its magnitude. Its direction was 45 degrees above the horizontal. So Kahaku, does that make sense so far? Everybody, does this make sense so far? Again, he's the one who asked for the problem, but this is for everybody. So then
Yeah,
continuing.
and actually, I want to point out too. I think it did say you could ignore the height difference between the ground and where the ball is fired. If you didn't do that, you still could do this problem, right?
Oh yes.
Because the height difference is just 5 centimeters divided by the square root of two, because it's basically five centimeters sine 45 degrees. And so that will give you some small change in the energy. So like you'd get a potential energy final, right? That was mg 5 centimeters sine of 45 degrees, which you'll see is a fairly small number compared to 1/2 kx squared. So it's totally doable. Like, so if you didn't follow that, if you didn't follow that, you could ignore it, right? Well, plus x sine theta mg, but yeah.
Yeah, you could do that. It's certainly not wrong. It just you'd have a little bit more algebra to do. And then part B, asking for the maximum height above ground. So this thing is then going to travel along this path, and you need to figure out how high it is at this point, right, where it's traveling purely horizontally. And there were a couple of different ways to do that. You could use plain old kinematics in projectile motion. You could use the work energy theorem. So you could say that before is at launch, after is at the top, and use the work energy theorem to say 1/2 mv initial squared plus the work done by gravity equals 1/2 mv final squared. So that's going to become, well, the work done by gravity is minus mgh, because we're trying to figure out that height. And then the final kinetic energy, it is still moving at the top, right? But here, its velocity is just the x component, because the y component has gone away. So this is v naught sine theta. So that's going to be 1/2 m v naught sine theta squared, because at the top, only the x component of the velocity is non-zero. It's the same as it was in the beginning, but the y component is has gone away. Actually, technically that should be cosine. It doesn't matter though, because it's 45 degrees. And then you can solve that from there conveniently. Cosine squared of 45 degrees is 1/2, and everything becomes real nice and simple. So any questions about that problem, or questions about literally anything else? I'll give you all a moment to type while I conjure my slides back up. Okay, I have some closing thoughts that I want to kind of give you all, and Matt, feel free to jump in on any of this. This is kind of taking our class and putting it in perspective, because we've been through a whole semester, and I want to kind of take stock of where we've come. It turns out that the things we've done in this class are way more powerful than you think. We've studied things where we can very easily do the math with pen and paper, in an exam problem or a homework problem. But if you take these ideas and extend them to other systems, you can, for instance, model how atoms push on each other. So a chemist will tell you that this formula is a pretty good approximation to the force law between, say, argon atoms. And if you put it into a computer and let it go, you can simulate, by simply changing the total amount of kinetic energy in the beginning, or adding or removing kinetic energy, doing positive or negative work on your atoms, you can watch these argon atoms freeze, melt, and boil. And all you do is F equals ma. You can even get the ideal gas law from this simulation and see the ideal gas law start to break down when the atoms become too cold to be ideal. Oh, hit the wrong button here. So what we're doing here is far more applicable to what you might think. You all are going to take Physics 2 in the fall, right? the biggest single piece of advice I can give you about Physics 2, and I've talked to the Physics 2 faculty about this, and I've tutored a lot of Physics 2, is don't forget that the work energy theorem and kinematics and all of these things apply to the electric force as well. Physics 2 is really just learning about two new forces and then doing the same stuff you already know with them. So what is the rest of physics? Well, Physics 212, what you will take in the fall or over the summer, is just another force. All you're going to do is apply what you've learned to that new force. You will get a little bit better at geometry because you'll need to think in 3 dimensions, and you'll see that light is just a manifestation of that. You might study thermodynamics or statistical mechanics, and that's really just how do I apply F equals ma to an Avogadro's number of atoms. You need a little bit of new math for that, but really that's all it is. Relativity changes how you think about coordinates. Quantum mechanics changes the way you think about matter. Now, matter is a wave, but ultimately you'll see that those waves, in their own way, obey Newton's laws of motion. And as you poke into physics more, each of these disciplines you can think about kind of in 3 different disciplines, 3 different mathematical perspectives. In this class, we have primarily concerned ourselves with theory, with doing calculations with pen and paper to try to figure out how things ought to work. But you also took a lab class in experimental physics generally, so not just thinking about even physics coursework, but thinking about physics in general. Of course, science is empirical. We design tests for our theories, we build machines, and we do these tests. This is what Professor Rudolph does when he's not teaching, right? What machine do you work on?
Yeah, so right, I work on LHCb experiments. Right now we're building, uh, silicon trackers. So you take these silicon, they're kind of like diodes, like a million, like thousands and thousands of diodes. If you ever done any circuit stuff, and when charged particles go through, they create little currents, and that's what you measure. So that's, I guess that's 212 stuff. But then that's telling us about, how do we actually test what happens when you collide really, really high energy particles together and produce heavy stuff that doesn't live for very long. And so I do, it's that whole bit, experiments, that whole bit where you have to figure out the technical bits of how you do it to actually connecting it to the theory. So,
And the physics of the machine often are as fascinating or more than the physics done with the machine, which I find to be an interesting property. Um, like the
yeah.
physics inside a particle accelerator is phenomenally complex and quite fascinating to me anyway. For people listening on YouTube, I apologize for the various glitches that you're seeing. I have something wrong with a piece of equipment on my end. You all live on Collaborate are not seeing this, but I'm kind of desperately trying to get some equipment to work on my end. Um, all right, I have to fix one thing. There we go. And the third kind of branch of this 3-legged stool supporting physics is computation. So doing computer simulations of things when pen and paper is not the even a feasible approach to the mathematics. This is my discipline. This is what I did in graduate school, and this is what I still do. So if you have any interest in computer simulations in physics, come talk to me. We're actually going to be doing a lot of that in 211 next year. So next year, students are going to do maybe half as much algebra, but instead of doing algebra all the time, they will be writing code in the computer language Python to solve physics 211 problems. So that's going to be an interesting change that we're going to try next year. Sorry, I'm trying to fix something. So I want to extend 2 invitations to you all here at the end of our class. A lot of people find this class to be fun. A lot of people find this discipline compelling, interesting. Many of you are doing very, very well. Like the grades this semester are super good. And I want to make sure everybody's aware of the other things you can do in physics at Syracuse University. We have multiple degree programs, so you could take more classes just for funsies, um, but you could get broader academic credit for what you're doing. We offer a physics minor. The physics minor is Physics 211, which you're taking now, Physics 212, which you're likely already going to take next semester, and then 4 more classes. We've got classes in the physics of living things. We have just hired some new faculty last year, and we're going to be hiring even more people studying the physics of living cells. Um, we have classes in the history and future of the universe called cosmology. So, where did the Big Bang come from? How did it work? Physics of stars and galaxies in astrophysics. You could take a class in computational physics in the fall, these computer simulations, studying how to use computer programming to do fancy things with F equals ma. There's a class in modern physics studying relativity, quantum mechanics, light, sound, a fancy lab class, and probably some other classes I have forgotten. So, Matt, do you have any favorite upper division electives you'd like to pitch?
I think you got everything. So,
We have a nuclear physics
uh,
class that may be coming back soon, actually. Um, I want to teach a class in the physics of music, photography, and how they connect to quantum mechanics. That may happen through the honors program soon. We also offer 2 different physics major programs. Um, the physics department really is the dark side, but it's also a supremely friendly place. Um, I have a close friend who works for another department, which I won't name in our university, and they were talking to me last night about how their experience in their department is very different than my experience in physics. Our department is a supremely warm and welcoming place. My experience has been, and many students find that as well. So if you'd like a friendly department to come study in, we're always looking for folks who would like to study more physics and get a degree here. We've got 2 degree programs. The Bachelor of Arts program um, is set up either as a double major or as something to prepare people for jobs in industry. It's a great double major with engineering, with education, with architecture, with film studies. We have one of those, with anything you'd like to do. The Bachelor of Science program is a little bit more technically demanding. It's the same as the BA program, but with 3 more classes added. And it prepares you to go on to PhD level study in physics or for the most technically demanding jobs in industry. If you're interested in possibly being a physics major or minor, please drop me an email, give me a call. I will be happy to chat with you about that. Also, um, Gilberto, you can see your grades on Blackboard. The grades that you can't see on Blackboard, you'll need to talk to your TA about. I don't know any more about your grades than you do. As soon as class is over, I'm going to send out the grade calculator Excel sheet that I wrote, so you can type your stuff into that. Um, so if you've done reasonably well in this class and you're pretty good at talking to people, like I've seen many of you are, we want to offer you a job. So you've worked with the coaches in this class. Those coaches are, the people who have been alongside you in your recitation, who have walked with you in your course of understanding all of this stuff. And next year, this class is going to be facilitated just by people like you. I've already approached some of you about being coaches. I see many names in chat that I have in the collaborate list that I've talked to. If you are possibly interested in having a job next year, helping your peers, get in touch with me. We are always looking to hire good people. This is a job that, this is a paid job. You don't need work study money. It's about $12 an hour, and we get you, your schedule is completely flexible. So come talk to us if that's what you'd like to do. Does anybody have any closing questions or comments for us? We have 5 minutes left. I want to kind of leave you with one last thing. if nobody does. Um, One thing I would like to do, though, is wave hi to you. So I'm going to, at this point, kill my slides. Um, may not be able to. Ah, the computer that I'm presenting on doesn't have a webcam. So the second computer one of me um, does have a webcam, but you may not be able to see it. Could you see that, Matt? It doesn't matter.
No, I don't see it.
Ah,
I don't know.
it doesn't matter. Um, the last thing that I wanted to do was to thank you all. Y'all have been a wonderful class. You've learned a huge amount of stuff that's actually pretty challenging, and you've handled this transition to this online thing that none of us signed up for with a lot of patience and a lot of grace. So um, thank you all for bearing with us as we try to figure out how to make YouTube videos and how to screen share and how to use a tablet and stylus, which I'd never used before. How to run Open Broadcaster Studio. So thank you for your patience there. Um, I know this isn't what y'all signed up for. I know this is not what any of us wanted at the beginning of the term, but y'all have been great with this. I hope to see you all in person again in the fall. One last thing, if any of you ever want help in Physics 2, come talk to me. I will give free tutoring for anybody in Physics 2. I have always done that since I've been here. So come come chat. Thanks, Kim. And thank you for all of your enthusiasm and good cheer, both in Astronomy 101, where there were a student last year, and in this year. Of course, Gilberto. Matt, do you want to say anything?
Uh, no, yeah. Thanks everybody for this went really well. I think it's the best semester I've had this, even with some of the technical issues that we went through. So I'm pretty happy actually.
Yeah, the
Um,
grades have been great, frankly. Um, I did want to leave you with two last quotes about physics in here, since I can't share with you my face. So my hair is even shaggier than normal. I haven't shaved in a while. I kind of look like a mess. Um, that's just kind of my default state, and even more when I'm working from home. Um, about what physics is. So the first quote from Richard Feynman is simply that science is the belief in the ignorance of experts. None of us know what we're doing either, and the best path to accomplishment in science is to keep asking questions of everything, because even the folks with PhDs drop minus signs and make mistakes all the time. And finally, Ernest Rutherford said that all science is either physics or stamp collecting. And what he meant there is that physics is really the most basic of any of the sciences, that all of the other sciences are built on the foundation of physics. So we kind of take a lot of pride in what you can do if you put your mind to it with the tools we have. Any last words before the end, Matt?
nope.
All right.
Maybe just good luck. Good luck finishing your assignments and with the exam.
Yeah.
Hopefully,
Thank you all so much.
and your other exams.
We have a bazillion review sessions. Please come to them if you have any questions about anything. Thank you, Lisa, Zachary, Alejandra. You all have been fantastic students. Lisa, by the way, I talked to our associate chair about possibly having you help us out with video production with all of your skills, and she is totally on board with hiring you to do that in the fall. Thank you, Savannah, Kim, Max. Annie, I appreciate your use of the word y'all as somebody from Alabama. Yes, I'm from the deep south. Yeah, there's no class on Thursday, Gilberto. This is Syracuse, for whatever reason, does a half week for the last week. I don't understand why. Ask the registrar. Our associate chair is also from Texas, Annie. She and I were talking yesterday about kind of our experiences as transplants from the north to the northeast. Where are you from in Texas? Ah, My partner's family are from Dallas. So, Matt, I guess we should hop off of Blackboard here and get on the other session.
Yep.
Right, I'm going to kill the recording.
All right.
I'll be a little bit behind. Something is wrong with one of my monitors and it keeps glitching in and out, so I've got something to fix.
Okay.